Hello, y'all. Welcome to lesson 76 in my DP chemistry curriculum. Today we're going over reactivity 1.3.5. A fuel cell can be used to convert chemical energy from a fuel directly into electrical energy, and we're going to deduce half reactions or half equations for electrode reactions in a fuel cell. Now, I do want to say before we actually begin this unit, this is a lot of what we call redox reactions or electron transfer reactions, which we're not actually going to cover for quite a while, but this is going to be a little intro to it as it fits better with fuels and fuel efficiency than it does with redox. And it'll be a nice little intro. So when we talk about creating electricity, usually you're doing something like creating a flame and you're boiling some water and then using that steam to spin a turbine. And through the rotation of that turbine or whatever, you produce electricity. Here is my picture of electricity. But that's really inefficient because you're creating that fire from a fuel, which is combustion, which a lot of energy is going to be released in the form of heat and light as well that we're not using. We're heating water, which then turns into steam and to rotate the turbine. Then we have a little bit of friction. We have loss here, there. And so the electricity we get is really inefficient. So what if we could kind of skip all that and we just go from our fuel straight to our electricity? And we can. This is what we call fuel cells. Fuel cells directly convert chemical energy to electricity. They're being a lot more popular nowadays. They're a lot more common, um, but they take a bit of requirements to get going. So the first thing we want to talk about fuel cells is they require a spontaneous reaction. So a reaction that's going to happen on its own. So a spontaneous reaction, and it needs to be divided into two separate reactions, or divided into two separate parts connected by a wire. Because what's going to happen is electrons in the reaction will move through the wire, creating current. This sounds really weird, but I'll show you what I mean as we talk about the two major types of fuel cells that the DP cares about. So the two types we're going to look at are going to be methanol fuel cells and hydrogen fuel cells. So we're going to start off talking about methanol. So I'm going to bring that down here. Methanol fuel cells. All right, so we kind of know the combustion reaction, so we're going to start out with this reaction, combustion. The combustion of methanol looks like this, CH3OH in gas plus 3 halves oxygen gas. And you'll notice I'm using fractional coefficients. I'll explain in a moment. That combusts to make CO2, also in gas, plus H2O, usually in gas. And this has a delta H of negative 711 kilojoules mole inverse. So it produces a lot of energy. We know that because we're getting minus 711. And on top of that, uh, we kind of know this reaction. We can control it. We're just burning some methanol. And one other thing I said I'd mention is we're using fractional coefficients. The reason I'm doing that is because I'm trying to look at per 1 mole of our fuel, because you'll notice we have mole inverse, so per mole. So I'm going to stick with the fractional coefficient so I can continue to look at only 1 mole of methanol. We can burn this, we can get this energy out, we can use it once again to heat water, which creates steam, which then turns a turbine and creates electricity. But there's a better way, and that is with fuel cells. So instead of taking this over overall reaction, we'll take it into two reactions and we'll divide it in half. So we'll call this a half equation because it only makes up half the equation. So the first one is we take our methanol, CH3OH, and what we're going to do is we're going to react it with water, which sounds a little strange, but with that we can produce carbon dioxide, 6 hydrogen ions, and 6 electrons. Now we have to do this in an acidic solution, but regardless, we are now going to get what we would call a loss of electrons. So this reaction basically strips electrons away from methanol, or specifically from the carbon in methanol. So we're stripping out these electrons. We then have a second reaction. So this is going to be half equation 2. And this one is our one with oxygen. So we'll take our 3/2 O2 plus 6 hydrogens, and we're going to add 6 electrons. And when we do that, we get 3 water. This is a gain of electrons because we're putting them in. They're in our reactants. So we are in total gaining electrons, and those electrons are essentially going straight into the oxygen. Oh, not there. Here. So we have names for these. When we lose electrons, we generally call this oxidation. When we gain electrons, we call this reduction. If you think about oxidation states, where the word oxidation comes from, the oxidation state decreases when you add electrons. It goes from a positive value to a more negative value. We learned about oxidation states quite a while ago, but if you look at oxygen here, its oxidation state is 0, and then moving into water, its oxidation state is -2, and we have 3 of those. So that means we had to gain 6 electrons. So this is a little bit of redox that we will return to in a couple units, but this is our equation. If we add these two equations together, you'll notice this water cancels with one of these. This 6 and this 6 cancel with this 6 and this 6, and we're just left with methanol, 3/2 O2 on the reactant side, and CO2 and 2 water on the product side, which is still our combustion reaction. The only difference is we put this on 2 separate sides of a reaction chamber. We have our methanol, CH3OH, going in with some water. We have our CO2 coming out. We have 6 electrons that will move across into this chamber. In this chamber, we're pumping oxygen in, and we get water out. And so through this reaction, we can actually measure the movement of electrons and get a voltage here. And this is what a fuel cell is. We just separate these reactions, and so that the only thing that moves through our reaction chambers are electrons generating electricity. So this happens all in an acidic condition so that electrons can move easily. We have free hydrogens moving around. We'll learn a little bit more about that as we get into our acid-base section. But basically, we are taking out all the middleman of turning chemical into electrical energy, and that's a methanol fuel cell. So that is methanol. With hydrogen fuel cells, it's a very similar thing. In a hydrogen fuel cell, we divide our reaction of hydrogen gas plus oxygen gas reacts to form to H2O, to water. That reaction is a very common way to create water molecules. And we divide it into, once again, our 2 half equations. So we'll start with the oxidation one first. Remember, oxidation being the loss of electrons. So our oxidation reaction is we take our two hydrogen gases and we just break them up in the presence of an acid into hydrogen plus, 4 of those, plus 4 electrons. So basically what we're doing is we're just stripping 4 electrons from our hydrogen. In our reduction reaction, or reduction half reaction, what we're doing is we're taking our 4 electrons that we just gained from the first one, we're combining them with oxygen gas, and we're combining that with, once again, 4 hydrogens, 4 hydrogen ions that we also just gained, and we get H2O. And so now that we've divided these reactions, we can create our reaction chamber. In our reaction chamber, we pump hydrogen in. We have a membrane which those hydrogen can pretty much access. We pump oxygen in, and we have our electrons move across. And here we get water come out. And so our electrons pretty much transfer from our left side, our hydrogen side, all the way to our oxygen side, completing the reaction, producing our water. And then all we do is we just use this moving electron to create a current. This is a current that we can utilize for anything we need to run with electricity. The final piece of this is that when we're doing reactions that have the movement of electrons, wherever oxidation happens, we actually call that the anode. So this side is the anode. Wherever reduction happens, we call that the cathode. I'm going to mention it now, but you can think about the abbreviation ANOX, like an oxen, and a red cat. I'll do that in red. Red cat. So you just think of a cute little red cat. And that's reduction. And you think of an ox. I'm going to try and draw an ox now. I think they have horns. And that's oxidation. So oxidation happens at the anode, and reduction happens at the cathode. So that is a fuel cell. That's pretty much the idea behind it. We separate out the reactants into 2 equations. We allow them to react via the movement of electrons through a wire, which we steal that movement of electron, that electricity, that current, and that's what we use to do things. And that's about it. This is a very efficient process, but people often say, if we're only producing water, this is great. Why don't we use it more? And so while it is clean and efficient, the production of H2 is not efficient. It is very energy intensive. Which makes sense because we get a lot of energy turning H2 into water, which means it would take the opposite amount of energy to turn water back into hydrogen. So it's very, very energy intensive. Furthermore, there are different methods, and some of them also can create harmful byproducts. So while we love hydrogen fuel cells and they work very well, they are still not the best technology in that to produce the reactants for it, it is very difficult, very costly, and can produce some harmful byproducts. Anyways, I hope this helps you understand fuel cells just a little bit more, and have a great day.